Okay. Thanks for coming. I know it's early morning, last day of the conference. I've seen even on the hallways, there's barely any people left. I think we have plenty of material to cover this morning, but I do have plenty of time to answer questions. If you want to interrupt at any point, I think it's maybe best if you interrupt during and ask in context. There's a mic there as well. You can even shout. Rather than wait till the end. It's maybe if the information is in context, it would be better. So these are some of the places where I've done some damage in the past and currently. So if nothing else, I'll leave you with this nice quip. It's not mine. If you're Star Trek fans, probably. So by the time we end the discussion, you will get why this is highly relevant for the context of the topic when discussing values in particular and properties about values and what we can do safely with them. So I'm hoping to tease some of these aspects with some examples and sort of maybe open up the discussion in even broader terms in what it means to do proper type design in general, and some of the tricky bits which relate to object relocation in general. So there's all sorts of classes that we usually write from simple wrappers, utilities, callables. We provide some other APIs, functions. We sometimes bundle functionality in classes, just like poor man's packaging format or namespace. We sometimes construct dynamic polymorphic types. They tend to be rarely needed and highly abused in most cases. We construct all sorts of containers, and of course, we construct things that kind of smell like values. So there's all sorts of things that we sort of put this umbrella of structure or class on top of, but they're very different in their semantics. Some are more special than others. So a while back ago, I did a presentation on the very same topic. And it was very popular at the time. And last year, a few people have asked me to sort of revisit these ideas in light of new developments in C++, specifically with C++20 concepts, and in the context of newer vocabulary types that came into the standard library. So I did just that. Sort of, it's like partially revisiting some of the fundamentals from last time and focusing on newer developments in the language. And of course, I have some parallels with other programming languages as well. When you talk about type constraints and sort of see how others deal with this kind of issue. I won't go into depth in other programming languages, so it's mostly a C++ talk. So let's get into it. So why are we talking about this? Well, regular types pop up almost everywhere, although not named as so in all places. They're foundational concepts in programming in general, in generic programming especially. And throughout the C++ standard, they're fundamental in how we define constraints on algorithms and properties about various collections and types. Even the CPP core guidelines spell out regular types in at least two guidelines, make regular types easier to understand, reason about, try to strive to make your types feel like built-in types or fundamental library types such as string or vector, sort of do what the ints do. I think we've all heard this one time and time again. And concrete classes without assignment and equality can be defined, but they should be rare. We're going to spend a lot of time today discussing equality and what it means, and in general, equivalence classes. Bless you. It's all that AC here, right? Okay, and there's one more related to template arguments. So it's when I started thinking about these topics and the talk particular more than 5 years ago, it was sort of after I dug into the original Stepanov paper from '98 on fundamentals of generic programming. Anyone actually read the original paper? Not one hand. I'm not surprised. It's not a really accessible paper, but it's not long. It requires some contextual knowledge. So I'm going to try to demystify some of the ideas there and present them in a more approachable fashion, hopefully, with concrete examples and recent developments. So the talk is not just about regular. In general, it's mostly about values and objects and concepts and ordering relations and requirements on algorithms. A lot of this talk is about equality. And when we talk about equality, whole part semantics is highly important. And we even touch a bit about lifetimes. And we already mentioned core guidelines. So, and as language versions spans many language versions from '98 up until most recent developments. Anyone seen Titus Winter's two-part talk on type properties and type family? Excellent, one hand, good. Link is right there. Highly recommend. I have, throughout the slides, I have many links, and I do recommend a bunch of articles and other presentations that I found very instructive. Some of them are known, and they're all very good. That's why I'm recommending them. So let's start with the beginning, and the beginning is really not in programming, rather in mathematics. And because we can't talk regular without talking about the man himself, Stepanov, I think this whole journey on defining categories and concepts in mathematical terms actually comes from really deep roots in thinking about number theory in general and about computing stuff, mainly starting from Egyptian multiplication and GCD algorithms and how they evolved and been abstracted over years. This is a very nice journey. It's a long thing. I think it's 30 hours or something, but if you're into this kind of stuff, really worth your time. So there's a series of lectures called 4 Algorithmic Journeys. There are actually 3. So I put a link there. It's, 32 hours of content. Enjoy. So if you want like a more condensed version, there's a book on the same topic. Yes, the book is actually more condensed. Sort of feels like a Hobbit situation, right? The book is actually way easier to read. Covers the same ideas from Egyptian multiplication up to RSA and cryptography, and how these concepts all tie together and various refinements over time in understanding of these concepts in mathematical framing. So it's basically the main thread of this book. And it has nice historical tidbits as well, like biographies and some side stories, which are enjoyable. So in the beginning, because we're talking about early beginnings of defining these numerical ideas, our beginning is just zeros and ones. And if you've been in Jonathan Mueller's talk, I think it was yesterday or 2 days ago, about object lifetimes, anyone seen that? I see 3 hands. Okay, good. More people should watch it. So first 7 slides from Jonathan's talk, you're going to see them again. But I claim I was the first. Yeah, I have these slides from 5 years ago. So it's very important. They're not Jonathan's. They're not mine. they're actually from elements of programming. So it's the formal way where we can establish some vocabulary that we can talk properly about these ideas without sort of misstepping around overloaded terms in programming. And people abuse sort of ideas and they call objects various things and sort of formalizing the vocabulary. So I'm gonna repeat that for the people who haven't seen Jonathan's talk. Datum is defined as a finite sequence of zeros and ones, and it can represent anything really in computers. That's why you do, right? From text to videos and everything. But they really don't have any meaning on their own. And the value type is the correspondence between these abstract representations and a set of datums in computer memory. So that's what we call value type. And a value is this datum together with its interpretation, because you can assign different meanings on how you encode these kinds of things. So the interpretation function makes a big difference. For example, an integer represented in 32 bits as 2's complement in big endian ordering has a value, can model a value, right? And most importantly, and this is, again, that's why we need to establish proper vocabularies. When we say values, we tend to think int a equal 5, we have the value a. No, that's not what a value is. A value is an abstract idea and cannot change. The value is, for example, 5. When we say 5, that's a value. It cannot change. What we abuse and sometimes call values are actually variables. So a value cannot change. And this is where we first start coming into equality and representational equality. If a value is uniquely represented in computer memory, equality implies representational equality, right? It's sort of self-evident. Conversely, if a value is not ambiguous, representation equality implies equality, right? If we have the same interpretation for that value. And an object, and again, probably a few folks who went into Jonathan's talk yesterday, and so object lifetimes, they probably expected stuff. I'm going to construct an object and I'm going to see destructors and constructors and stuff. Objects are not like OOP objects, right? There's representational of these concrete entities as values in computer memory. So as defined by their address, length, alignment, and so on. So that's what we call objects in the most general setting. And an object has a state that is the value of that type at that moment. So this can change. For example, we can put something other than 5 in that object. Type is a set of values with the same interpretation function and operations. And the concept is grouping several of these things that are related in some way. Again, all these things come from elements of programming. You can still buy it, I think, in paperback, but if you prefer convenience, you can actually download it for free. The subjects of this presentation cover 3 of the chapters in the book that I highlighted there. The book is not really accessible, so I recommend you start with stuff like this and then maybe go to the book if you have the stomach for it. The first one I mentioned, From Mathematics to Generic Programming, that's actually a very accessible book. Elements of programming, you need to build up to it and read it several times. Another series of lectures that I found very nice on the mathematical underpinnings in generic programming is this one. Very few people are actually aware about this one, so that's why I keep sharing it. And of course, the obvious thing is, I've been programming for a number of years and I've never needed any of this crap to deal with it. So I managed to do it. Why do I need to bother with this thing, right? Why are you wasting my time? So the reason that things that just worked is because others have bothered with this stuff. And they thought long and hard about it, and they designed the types and the libraries that you're using so that they feel natural and intuitive for you to use. So the reason why you didn't care is because others did. But you should care too. And because you are going to interact with these things, and at some point, some of your assumptions might not be met, and you're going to design things yourself, types and utilities and stuff that others are going to consume, and you're going to break their expectations. So you sort of need to align with the context. So again, this is the original 98 Stepanov paper. I'm going to extract just a few bits. I'm sure you're not going to run away from here and go read it. So I'm going to extract just a few bits from it. So generic programming depends on the decomposition of programs into components, which we maybe developed separately and combined subject to well-defined interfaces. And very relevant to the topic at hand, among the interfaces of interest, fundamental operations to all common C++ built-in types and user-defined types are copy constructors, assignment, and equality. So, and like I mentioned, I'm going to spend a lot of today's time on equality. So the paper actually investigates some of these relationships and consistency and semantics, and again, what people expect sort of coming out of mathematical training and logic, and what do they expect when they meet these kinds of ideas in computer science. So again, it's all about meeting expectations of users and building something that's simple to use, powerful to model difficult ideas, and enrich sort of your custom types with properties, with additional properties, but without breaking these expectations and intuitive usage. And yes, simplicity is a good goal, because you might be comfortable with the details because you feel like you understand them, but no, like I said, no one really has the time to revisit all the fundamentals when they need to deal with that API that you provided. Or so they sort of expect, oh, if I'm gonna compare these things, or if I'm gonna pass this lambda or this predicate to your function as a predicate, I'm gonna expect that it will work as I've seen other things work in the past, sort of, right? Don't break my expectations. So even if you feel like you built a very clever thing that accomplishes what you wanted, I think it's unproductive to expect that someone else will be willing to work with that thing and extend it further. I was waiting for Anastasia. Yeah. Okay. So if you if you're not sort of convinced to read the original Stepanov paper, this is a much more accessible version, a much more recent one by Titus Winters, sort of an analysis of the same ideas, but in sort of more condensed and modern approach, maybe. So start with this one. Yeah, and of course covers new stuff. Anyone seen Lucian's talk yesterday on hylomorphisms? I see a few hands, very well. So we already saw a clip from this presentation in Lucian's talk. I do recommend you see the whole thing. It's super interesting. Not very technical, sort of more of a contextual historical thing. Very nice. So some of the fundamentals we need to build up to this equality thing. So fundamental principles behind STL itself, because we're all tying this to STL types and algorithms. So the guiding principles here are about identifying and organizing these algorithms and data structures, finding general representation of them, sort of, that's the whole templates thing is about the general representation. The concepts idea is about the general representation of these things. So Again, whole part value semantics, very, very important piece of this discourse. And of course, something that by now we've become accustomed to, but back then it was sort of revolutionary, this decoupling between algorithms and data structures through this abstraction of iterators. We take it for granted nowadays, and we even shun to say, oh, iterators, yuck, ranges, give me ranges. But the idea is a fundamental change in how we think about setting general functional pieces like algorithms. I don't think there's anything new here. Okay, so some of the important bits about how we design data structures themselves. They sort of have to match the semantics of C structures, because this is what we inherit, this is what we need to interact with. So STL types cannot depart too far from the object model of C. And again, when I say object model, I don't mean anything that comes from the 2000s era. So two objects should never intersect. There should be separate entities, and they should have separate lifetimes. More on that later. And I've been saying this, I think, over 10 times by now, whole part semantics. What that means is that if you copy an object, you have to copy all its parts. And when the object is destroyed, all parts must be destroyed. And two things are equal if all they have the same parts, sort of all the way down, their corresponding parts are equal. Seems like, oh, it's a no-brainer. Of course, this should be, but this is not how we usually build software, unfortunately. By far, my favorite presentation, and I've seen a lot on value semantics, is this one by Dave Abrahams. And of course, a lot of the content covers things like whole part semantics. Some hints to the Val programming language, now Hilo. So well worth your time to learn some of these interesting ideas. So it's sort of like theoretical underpinning, revisiting really old concepts like I do now, plus some hints about novel ways of thinking about them. So lots of sort of hidden hints about Hilo. Generic programming, as it started and even today in C++20, has some drawbacks. And the things that I care about in this context is about requirements on algorithm types. And traditionally, these have been sort of agreed upon through documentation, through preconditions, so by specification. But there was no formal mechanism to actually enforce them and get any kind of good diagnostics out of using them. Some examples are on this slide. So these named requirements are sort of used to define the expectations of the standard library and how it's supposed to be used. And people think that all of them have been encoded in C++20 concepts, but that's not true. A lot of them have been encoded in concepts, but not all of them. Some examples, just a few of them, there's plenty more, especially concepts in the iterators library and algorithms library and so on. Ranges, of course, bring a lot of concepts. So just some examples. I maybe picked some examples that are relevant to our chat. So what is a concept anyway? Anyone actually using concepts before, right? Not one hand. Okay, it kind of expected that. So concepts are a formal specification that makes it possible for compilers to actually verify that the arguments you provide to templates match the expectations of the designer. And that happens during overload resolution and template specialization. And concepts are just predicates. There's just like predicates that we compiler can check at compile time. They can be composed, they can be really simple, or they can be really aggregate, complicated concepts. Syntax of defining them might be a bit, I don't know, bit weird, but in general, they're fairly readable. As you're gonna see, I'm gonna show some simple examples. So again, going back to the question, like, why are you wasting my time with this? Well, of course, if you're building such utilities that are to be consumed and shared, then that's a no-brainer. You're building stuff that others are going to consume. You want to sort of meet them where they use it and give them nice diagnostic messages and prevent unintended use and so on. But if you're just consuming, you might say, hey, then I probably won't care. Even when you get such a diagnostic from consuming one of these utilities, either STL or some other implementation from maybe your colleagues, you're going to scratch your head possibly to understand, you're going to get diagnostic that you don't meet some kind of predicate, some kind of condition in one of the concepts. But you're probably going to scratch your head into, okay, what do I need to do to satisfy this condition, right? If you don't understand the ideas, it's going to be harder to navigate, sort of, because all these concepts tend to be sort of composed out of each other. Sort of, you need to drill down to see, okay, what am I missing? What operation I'm not providing? What am I not satisfying there? Yeah. So let's pick just one simple algorithm. I think one of the frequent used ones in STL, sort. And we immediately see a compare thing there. And what are really the requirements for this compare thing? Well, of course, it's supposed to be something that's callable, and it needs to look like some kind of predicate. And because we're comparing things, needs to be a binary predicate, means taking two arguments, right? So it's probably has to look something like that. And if you go to any CPP reference page that deals with this kind of thing, you'll probably see an example. So the problem is, okay, I'll implement something like this, but the idea is, what am I going to put inside there, right? What kind of relationship do I need to provide for these elements of these collections that I plan to sort? I'm not, I think I'm the only presentation at this conference that doesn't have DALL-E or ChatGPT generated images. I actually have hand-drawn stuff. I should actually try to see what generates for this kind of shit. Anyway, requirements. So people tend to generally, I think, instinctively, I've asked this a lot. I've asked this with students, I've asked this with colleagues, and I would say that the first tendency is to always reach out for something that falls into the partial ordering side of things. I don't really have an explanation why people tend to instinctively go for something like this, but it's easy to build an example, like you see there in the picture, where a partial ordering relationship fails to define proper ordering that can be used with something like a sort function. So if you have like 3 points there, you can see that you can precisely, if you define a predicate like the one under the picture, you can say something about P2 and P3, but you have no way of saying something meaningful about ordering either P1 and P2 or P1 and P3, because according to that thing that most people tend to instinctively write, you cannot decide on ordering between them. You cannot say which goes first, because that's how you defined the relation. So we say that this, because you cannot have an outcome or decision outcome, we say that P1 and P2 are equivalent with regards to this predicate, and P1 and P3 are equivalent with regards to this predicate. They're not equal, but they're equivalent according to this constraint that we imposed. So what the piece that we're missing is transitivity of equivalence. One time when I did this presentation, I said, obviously the piece that we're missing is transitivity of equivalence, and somebody in the room actually laughed out loud. So I'm not going to do that mistake again. And by equivalence is what I described in words about the red lines in the picture. So equivalence means when we compare both directions, we come with the outcome false. We can't decide. So we say, if we can't decide which one is first, according to that comp function, then we say, with regards to that function, they're equivalent, right? And transitivity, I think that's the one that everyone understands, right? So again, throwing some math at you, just the names should be sort of familiar from, I don't know, middle school mathematics. Sorry, let me do a quick break. So irreflexivity, antisymmetry, transitivity, and this thing that was missing, equivalence. So let's see it in real code. Let's see this, forget about this math stuff. Let's see in C++ terms. This is like really a screenshot from CPP reference. So we see the same ideas I had in the tables, sort of expressed in documentation form, let's say. And one particular sort of specialization of this idea is less than comparable. The only difference here being that we replace the generic comp idea with the less than. And in many situations, this turns out to be sort of more practical, right? We tend to put less than between things, even if they're not usually compared with less than, right? But the same things, so the same definitions otherwise. We just replaced comp with less than. And if we go back to the previous list of named requirements on algorithms, we see, of course, one that sticks out and we need to deal with, equality comparable. We need to figure out what that thing is about. Again, going to maybe 5th grade or something, I think I vividly remembering some of this pain from 5th grade. These are the things we generally tend to associate with equality, reflexivity, symmetry, transitivity. These are the things that people expect when they talk about equal. And indeed, if we look at, by the way, this is how a concept definition looks at in C++20. So I highlighted the important bits in blue there. So if we look at the weakly comparable with, which is sort of the building block for equality comparable concept, this is the kind of things it checks. It checks if you have equality and inequality defined and symmetrical, because it makes a difference. So I want to highlight a bit about the difference between equality and equivalence. So again, equality means when we put that sign, like those double equals between stuff, even if we have a custom implementation, whereas equivalence is that thing that we saw originally when we talked about the points and we couldn't decide which goes first. So equivalence is sort of a more general setting, and equality is just a special case. And anyone can give a maybe simple example of when we would distinguish between equality and equivalence for a type? Anyone? Something, I don't know, can be a toy example, where you want equality to mean something and equivalence to mean different things. Something? For example, we might have, think about looking something up, let's say some some string-like thing, and you want to look it up regardless of its casing representation. Let's say you're searching something on a web page, you're searching a contact in an address book. Yeah, you want to look it up, and you don't care if you spelled it with the correct uppercase or whatever, for the first name, last name, right? They're definitely not equal as string representations, but the semantics for that operation is that they're equivalent. I don't care. Give me everything that matches, regardless of case, right? For that operation, so for that comparison, you care about this equivalence relationship. So they're definitely not the same thing, right? And there's plenty more examples, right? All right. Sometimes when you look at specifications about STL algorithms, you sometimes see this thing mentioned, total ordering relationships or strict total ordering. So it's the idea here is that it's a strict weak ordering relationship on the less than comparator. So not in the general terms of partial ordering. So I think most of the situations fall into this kind of thing. So that's why you tend to see it mentioned in documentation or specifications. But it's the same idea, strict weak ordering, but with less than. You can, in simplified terms, you can think of it in that way. And if you look at the totally ordered concept in C++, and you look at the operations that they're expected to exist, now whether those operations actually do what they're supposed to, that's another thing. But at least they're expected to be presented in this way, right? To exist in this way. If you decide to, I don't know, change some global state when you do less than, that's on to you. So the STL all throughout, and there was a very nice report a few years back, sort of like an evaluation, sort of like an audit of everything in STL at that time, and sort of what assumptions are made about the things in there. So STL assumes equality is always defined throughout, or at least equivalence relations that I mentioned. So whenever you decide to go against this and say, I'm not going to define equality here, you're going to have many places where you're not going to be able to interact with STL stuff. So either types or algorithms in there. So again, if you decide that you're going to build something that is not a proper regular type, and I'm going to show some examples, even from the standard library, they're not going to properly work in this context. So if you want everything to play nice, you have to play by these rules. Whenever you decide, I'm going to go on my separate journey here, then you will have to expect some pain and some friction. And we've made these mistakes even in the standard library. There's some stuff that it's not playing by these rules. But let's see what this regular thing is all about. Again, it's about some concepts bundled together. So semi-regular is defined by these requirements. In general, looking at these kinds of things, we sort of expect these to be either implicitly defined for us, or we generally tend to define them for types. Oh wow, the talk finished really early. Okay, so there's questions about if you want something to be default constructible or not. So there's some arguments to be made about that one. There's situations where you don't want to impose that thing on users. So that's maybe the asterisk one, and I'm willing to have a chat maybe afterwards if you're interested in that. Formal definition in C++ 20 concepts looks like this. Again, the same idea, just translated in syntax mumbo jumbo. And regular just adds this equality. That's why this equality is the most difficult part in this discourse. In this whole presentation, I'm focusing a lot on equality, because this is the controversial part. And this is the part where people mostly violate things, not the other things. So again, looking at how it looks in C++20, again, I highlighted the important bits there in blue. The operations that are expected. We see the stuff we've been discussing in mathematical ideas, like weakly equality comparable, combined with semi-regular, which we defined previously. But that bit with the equality, this is where it gets hard. So a quote is from the original Stepanov paper again. Two objects are equal if their corresponding parts are equal, applied recursively, including remote parts, excluding inessential things. So it sounds like it's a very convoluted sort of hand-wavy definition of equality, and it is. Because when you define this thing, you have to think about the semantics of the object, because you might have fields in there that you don't want to make part of the equality of that object. They might be part of the representational form of the object, but you might not want them to participate in equality. Think about some kind of maybe unique identifier or some caching thing or some remote part of that object, some remote observer or trigger or something that's not semantically part of that object, but happens to be in there just for housekeeping reasons. Again, not a sign of great design. So yeah, it's even Stepanov sort of hand waves definition. But we do have to deal with it, because we have this thing, three-way comparison in C++ since C++20, commonly called the spaceship operator. Anyone actually using it? I see a few hands. Okay, good. This thing sort of automates a lot of this boilerplate, saves you writing these all these functions that you've seen in the axiom tables. So it automates a lot of things. It's very convenient. You can equal default it. I would say, and of course, things that are returned are not just they're not just booleans or less than 0, greater than 0. It's not a simple thing. It's like all things we build in C++, we tend to over-engineer them. So this thing is a beast, and the most interesting bits are these ordering modes and how you treat equality. And again, if you didn't slip through the presentation so far, this shouldn't be foreign ideas. Watch out for weak equality there. That's why I put a fire there. So try not to model things in that way. You're going to get surprises. But even this thing initially had a very different flavor. And later on, people figured out that the initial design was not quite great, fortunately in time. And I even linked a paper there by Barry Revzin, sort of analyzing some of the problems and proposed solutions. And again, surprise, surprise, the problem was around equality. Because less than, greater than, everyone agrees how to deal with that thing. Equality, again, brought some problems. So as it stands out, you really, if you use this kind of thing, and if your types do any kind of expensive stuff, or they have some kind of nested collection type, or they have any kind of thing that you might suspect might be a performance problem, you better define equality yourself. So you can actually define three-way comparison and provide a custom equality, and you should. Why? Because performance. Let me show you an example. So if you were to sort of equal define such a thing, equal default such a thing, and you can, you would probably get something like this. Let's say you're providing this for something that has to deal with a vector of stuff. And this is how it would operate on a vector, right? I think looking at this code, just assuming that compare three-way function does the right thing and returns one of those types that I've shown here, returns one of those things. So just looking at it, it's looks like it's doing the right thing. The thing that is missing here is that it's doing extra work. And can anyone figure out what's wrong here?
Check the size.
Yes, yes. That's what's missing, a short circuit on the size. So that's why you need to, when you provide less than, you say, oh, I want to less than these collections, then there's no point in short circuiting. You have to sort of compare, right? But if you're thinking about equality, there's no point in starting to member-wise compare if they have different sizes, right? And it's not a correctness issue. If you write unit tests, you're not going to find this kind of stuff because it passes. So this thing passes any kind of unit test, unless you write sort of a unit test that tries to be sensitive to timing thing, right? For example, you compare a vector of a million elements with a vector of 1,000,000 plus 1, right? Then you're going to probably see this kind of thing. So that's why you need to come in with defined equality operator to be able to short circuit. These ideas appear in other programming languages as well, that I'm familiar with, for example, Rust and Swift. They both have the same ideas of concept things. They're called differently. In Swift, they're called protocols. In Rust, they're called traits. They're not like C++ concept, really. So if anyone remembers the original C++ OX concepts proposal by folks like Doug Greger, way back in 2010, I think. So traits and protocols in Swift and Rust are closer to that proposal, not with the concepts light implementation we have in C++. But when thinking about these kinds of things, about equality, about ordering, they all think about these ideas. There might be slight differences. For example, I mentioned default constructor. Swift doesn't have any requirement of default construction because of guaranteed initialization and the way they don't really have the concept of constructors. And you can define the same kind of operations and conform to these protocols, or in this case on the slide, Rust traits. So again, partial ordering, again, should be familiar by now. It's an equivalence relationship that requires symmetry and transitivity. Equality extends this partial equality with reflexivity, right? So to complete the axioms. Partial ordering, again, is modeled through this ordering enumeration in Rust, and ordering, which is the total ordering, which I showed previously. So if you look at the same example with the vector, but sort of in Rust speak, you don't have to understand the syntax, maybe the details, but you can squint and see the same kind of mechanics about the thing. And this is how you specify type constraints in Rust with that where clause. I seem to be lost. I lost the focus for a while. Okay. So some examples of things messing up this stuff. String view. I think I'm not even gonna ask. I'm pretty sure everyone is familiar with string view or even using it. Problem is that string view succeeds very well as this drop-in replacement for constraint graph, and it was designed so, right? But they're very different things. So string view is not really of a value type, and it doesn't project itself as a reference either. So it's sort of a weird thing where it sort of pretends to be a value, but it's not. People have been calling it this kind of borrow thing, borrow type, sort of stealing the idea from Rust, but it's not the same kind of concept. So what does it do? So it definitely lacks any kind of ownership over the thing that you're constructing for. They generally tend to be short-lived. They generally can do without an assignment operator, and people rarely do assignments with it. They generally appear only in function parameter lists. Generally, you can't safely use them in data structures or return them. So there's like real gotchas and linters and stuff that will scream at you if you do these kinds of things. So generally, like function arguments, short-lived things where you do some processing. Again, what's the interesting bit? The interesting bit is related to equality and assignment and what it means to assign something and compare something. So string view is assignable. I don't know how many people actually do this, but it is assignable. But the assignment has shallow semantics. So because the underlying strings are viewed as sort of immutable. String view is a sort of refers to something that's an immutable string underneath or buffer, right? So definitely shallow semantics. But the comparison has deep semantics. It actually does a lexicographic compare. So again, this is a disconnect between what we've seen so far about this whole idea of equality and Stepanov preaching, right? So shallow assignment, deep comparison. Because people expect when they do these comparisons that they compare the actual underlying strings. So when the underlying data is still extant, and because it's constant, we can determine by the usage that it sort of looks regular, right? Although it's not technically regular. So when used properly and sort of in idiomatic ways, so people kind of know by now that where it should be used. So for example, in function arguments, you kind of squint and pretend it's regular. And they're not going to be surprises, but it's not. But this beast, span, which people usually tend to, because it came after string view, they sort of think, oh, it's the same kind of idea, but for bytes, right? Not for strings. So they think of it, oh, it's an array view. But the problem is that the underlying data is mutable this time. And that's the whole idea. I mean, you want to deal with these spans of bytes and do something to them, right? So that's a fundamental difference. You can't treat it as you treat string view because of this fundamental thing of the underlying buffer being mutable by design. And again, same idea, span does not manage the storage. Lifetime is left up to the user, so you have to, by construction, provide the guarantee that the underlying buffer is still extant while you deal with this span or pass it around. So let's analyze this a bit. That's what it is. So overloading operators can be dangerous when you change the common meaning of the operator. I think I've said that a couple of times today, right? Meet the expectations. the meaning of copy construction and copy assignment is to copy the value of the object. Again, you have to think about, does this object model a value? What's the underlying semantics of this object? The meaning of equality and comparison is to compare the value of the object. Don't do something else when you implement these operations, like say operator equal and do something else. The meaning is to compare the value, not do other things, call some function that does some thing, right? That's what it's supposed to do. It's not supposed to have any either meaning or side effect. Copy assignment, equality are expected to go together and act as built-in types. Where possible, when designing types, design them as regular, right? So let's see this in the context of span, how these pan out for span. And by the way, this analysis actually happened during span standardization. So initial span proposal was different than what we have now. So copy is shallow. So just the pointer and the size are copied. Again, the idea was that you want to pass these spans around and should be cheap to copy and pass around, sort of like handles to the memory, right? You're not supposed to copy the underlying buffer. So we could make equality deep, sort of to compare the span elements with standard equal, and this would sort of behave like string view, right? Do a deep compare, sort of compare the underlying buffers. However, string view can't modify the elements, and a shallow copy of string view is similar to sort of, you can think of it as sort of a copy on write optimization. So, and fundamentally, is span really a value? Do we need a deep compare for such a thing? Like looking at the window into some bytes, do they always represent a value when you're moving that window through this byte buffer? Do they have a meaning on their own? They could, but do they in general? Because we're modeling a generic concept here in the standard library. So standard span is trying to act like a collection of elements. So sort of conceptually, it fits the idea of, oh, it's sort of like an array thing, sort of like a collection of things. But it's not regular, so it has reference semantics. That's the whole point. So also deep comparison implies deep constants, logical constants, sort of to extend the comparison to all the parts. What it means like logical constants. So all the parts of the type that constitute sort of participate in the value. If they participate in the semantic of the value, they should participate in equality and copy operations, because equality and copy should go together. They have to sort of work together. Deep equality means the value of the value of span are the elements it spans, not this pointer and size thing, right? Remember when we talked about, should it be cheap to copy around and pass around as if it's a handle? Or does it mean to span? Equality should span within the elements. So if we want span to act like a lightweight representation, then we need to have this shallow equality, just like we do for smart pointers, for example. By the way, people sometimes compare these things to sort of, they think of them, oh, it's some kind of box, like a smart pointer. So shallow const implies shallow equality. But shallow equality might be really confusing, because we've seen another thing that sort of looks similar, but doesn't provide shallow equality. So shallow equality sort of fits the design ideas of span, but it will definitely fail the other criteria of meeting developer expectation, because they've seen the string view and sort of might expect the same thing. I don't know, if they're not careful. So the only outcome of all these contradictions were just ship it. No batteries included. You deal with it. So that's what we have now. So we have a span type that doesn't have any quality, right? So definitely not regular. So it's a strange beast. Users can generally expect to interchange this with a vector or a standard array, and it happens to be the case most of the time. It just magically works, right? Until you try to copy or change its value, then it stops being nice with you. So it's semi-regular. It's this sort of weird thing. If you want to see some really cursed examples and ideas, read this old blog post by Corentin Jabot. Really, it's a really good read. Really cursed stuff in there. So for these kind of non-owning reference types, like string view and spans, you can't just judge them in isolation. You need contextual information. Whenever you see such a thing, imagine seeing a diff in a PR, and you see some change that involves something with this kind of span. And you can't just look at that diff and say, oh, I think it's all right. No, you kind of have to see the underlying context. We have to judge the thing, how it's used, to see if, okay, is the underlying thing still extant? How is it treated? Is it supposed to be treated? Is it supposed to be equal or not? Who owns it? Who sees it? Who modifies it? Sort of, you need all this contextual information to reason about it. All these things: shallow copy, deep compare, const mutability. Do I need to compare these things? I'm going to write something custom. Is it something that's doing the right thing if I implement it by hand? So they have reference semantics, but without any of the magic that makes constant references safer. For example, lifetime extension. If you look at this really trivial example, and in more complicated cases, not that obvious. If you just compare them and say, oh, it's just string view is just like a replacement for a constant string reference, right? If you look at this example, it clearly doesn't do what you expect, because string view will not do lifetime extension for a temporary return from that function. And the funny thing is that might even work, because if the string is short enough, it will be in the local string buffer rather than being on the heap because of small string optimization. So you might not even see it all the time. Fortunately, there are linter checks that can check for this kind of thing. For example, in Clang Tidy and other products. So in general, I would say if you want least surprises, make your value types regular. First of all, make types that are values and avoid just inventing stuff that looks like values, but they're not. But definitely make them regular. And again, remember all these other things, default constructible, copy constructible, all the other things, you're not going to run into surprises there. But you are going to run into surprises with assignment and equality. So that's where you need to pay attention. From all these concepts and things and requirements, you need to think really hard. Do I provide assignment? Do I provide equality? If I let the compiler generate assignment or equality, am I okay with the generated version? Does it do what I need it to do? If not, let's suppress it. Let's be deliberate about it, not accidental about it. So best regular types are those that model built-ins, they have no dependent preconditions. So if you have to explain a lot of things, like when using this thing, you should hold the hammer in your hand and lift up your leg and whatever, then it's probably the sign that it's a complicated thing. You should probably redesign it if you have to give too many explanations and preconditions. So think about string and vector. I think they're the only sanely designed things in the STL without any additional baggage. For non-owning reference types, like if you do need to construct things like this, these kind of handle types, handle things, you need contextual information, no doubt about it. And if you don't want to trick your users, just be honest about it. Just make them semi-regular. Just don't pretend to, don't give people false expectations. Just deliberately restrict operations. Do not provide equality. Do not provide assignment if the semantics are dubious. Just don't do it. Okay, that's about it. And we have sufficient time for questions, I think. Yeah.